Um, this is another one of those where it's like, why? I don't want to share it now. Stop share. Sorry. Sorry. Okay. It's like, why is this topic being brought up right now? Because we haven't even talked about some of the words in the topic. Like they relate to something different that we need to teach before we really talk about this. So, not going to spend a lot of time on it right now, but we'll go ahead and get introduced to it since that's the way we're doing things. Okay. Um, okay. I was just thinking that I hadn't emailed this to you or sending it to Google. I just did. All right. I'm going to share my screen mirroring, Zoom. I do all these on Zoom. You're not seeing it? There we go. Okay, so this topic is called free energy, all right, which you're going to see. It's not what it is called. This is copy and pasted from your notes. It's called free energy of dissolution. Guys, why do you have to use such words, right? There is no reason that we need to be using these words. Dissolution, forming a solution. Okay, that's all. Dissolving. Dissolving. All right? That's it. That's it. So free energy, however, is delta G. Okay, and we're not talking about delta G right now, so it's very frustrating that I'm expected to do that right now. So if you see right here, we've got delta G, free energy. Okay, and I'll try to get here enthalpy, and another substance which we haven't learned about yet and won't until Unit 9, same with delta G, is something called entropy. So I don't want you to stress too much because I'm not teaching all this right now. But what you can know here, and let's look at the words that are provided to us. The relative thermodynamic favorability. What does that mean? Spontaneity. That means spontaneity. That means, will a process occur without outside intervention? Will it occur spontaneously on its own or not? That's what thermodynamic favorability means. If it is thermodynamically, we'll talk more about that later, favorable, then it will, the process will occur without outside intervention. That does not mean it will occur at a quick rate. That is a kinetics issue, but it will occur. It could be carbon atoms forming diamonds and take millions of years, or it could happen like that. That's for kinetics. This is, will it happen without outside intervention? Okay. The answer to that is dependent upon the sign of delta G. Delta G is our free energy. Okay. If delta G turns out to be negative, then yes, it is spontaneous. If delta G turns out to be positive, then no, it is not spontaneous. But it would be in the opposite direction. Oh, okay. Now, what you see next is a different delta G. It's got that little knot. But that's basically the same one. That just means it's standard conditions. We'll look all into this later. Okay, so delta G standard, 1 molar, 1 atmospheric pressure. Okay, now the sign of delta G is dependent upon both the enthalpy, dependent upon, it's just so frustrating to be teaching this when we're not in thermochemistry right now. is dependent upon both enthalpy, delta H, and entropy. You don't know what entropy is yet, but that is delta S. All right. Entropy is a measure of disorder, but I'm going to have to teach you to not use that later. All right. Greater arrangement of particles. Okay, let's kind of finish this up. So we can have positive or negative entropies. We can have positive and negative enthalpies. So we are talking about the free energy, the delta G of a solution. Free energy is the energy available to do work. And any spontaneous process, the energy available to do work decreases. All right. So we're talking about the free energy, whether it's positive or negative, for the formation of a solution. Basically, we're talking about whether or not a formation basically, we're talking about whether or not a solution will form. Okay, if delta G is negative, then it will. Okay, so it depends on the sum of three independent factors. The enthalpy does. The overall delta G, as I just stated, depends on both the enthalpy and the entropy. The enthalpy is simply based on the sum of three independent factors, separating the solute, endothermic, separating the solvent, endothermic, interactions between solute and solvent, exothermic. Okay? The overall enthalpy here is dependent upon the magnitude of these values. We literally add them up. If there is a very great attraction here, then that negative value will override those positive values and we'll have a negative delta H. Thermodynamics favors negative delta H and spontaneous go together. In addition to these enthalpy changes that we've discussed many times, we also need to consider entropy changes. So changes that are talking about a measure of disorder or the arrangement, the number of arrangements of particles. When a solute dissolves, the entropy increases. There's a greater, what's the word I'm looking for? I don't want to use arrangement. There's a greater probability of finding particles in different places. There is greater disorder. So until I can come up with the word I want to use, I'm going to just use disorder. Greater disorder when a salt is dissolved as opposed to being in its solid form. Okay, and I know that this probably doesn't make sense to you, and when it's appropriate, it probably will. So delta G, the overall determining factor if something is spontaneous or not, depends on the enthalpy and the entropy. So we have the separating of the solute, the separating of the solvent, the combining of the solute and solvent, and the factor of whether or not this increases or decreases entropy. And in fact, it does increase the entropy. All right. And that's a positive delta S. You see it says C, thermochemistry, that the value of delta G and ultimately the thermodynamic favorability of any dissolution process. So we'll talk more about it is what that's saying. And I'm going to leave that at that. There are no practice problems here because it doesn't belong here in our content. All right. Thank you. On to Unit 8.